I too would like to thank, is this too loud? Both Barry and Bala for, putting together this workshop. It's been a wonderful discussion. I've been enjoying, almost every moment of it. And thank you to ITAMP, of course, for supporting this effort. I think this is a very important discussion that we should have more often, perhaps. And hopefully something will come out of this in the form of a proposal and a more concerted effort. And I would be more than happy to participate in whatever there is to come. Well, this is nothing. This is dying. So this is nothing to do with machine learning, but I wanted to put this up because the official publication date of this book is tomorrow, and I thought that there may be a few people in this audience interested in this book. So if you are, please let me know, and I'll be more than happy to send you a copy. So it took me 5 years to write it, but it's here. I'll send you a free copy. Really? Yes. Oh, perhaps I should take it back, but I'm happy to see so much interest. I'll be more than happy to send you a free copy. I'll pay for it myself and send it. Yeah. Right. So what I'm going to be talking about today is molecular scattering calculations, elastic, inelastic, reactive. I don't need to tell you why these are important, and there's a lot of reasons why we want to be able to do molecular scattering calculations precisely, ranging from pressure standards to applications in astrophysics and chemistry. I'm not going to say anything about that. So generally, all of the molecular scattering calculations that we've talked about over the past couple of days, they start with computing the potential energy surface for the molecular system, the collision complex of interest. Then this surface is generally fitted to some analytical form, and that fit is then used in a quantum dynamics code to compute the observables. Now, this process is quite complex. It often requires more than just one expert to do. We usually combine experts in producing potential energy surface to do the first two steps, and this laser pointer is quite useless. But and experts in quantum dynamics to do the dynamical calculations. And there are also problems with each of the steps in this. Oh, thank you. With each of the steps depicted here. Oh, perfect. So the potential energy surface calculations, they always come with errors. A lot of times these are unknown errors. We had a debate about this yesterday, and these errors, they propagate throughout this process, and a lot of times they affect the dynamical observables in a way that we don't know how they affect. Wonderful. Now the dynamical calculations are very time consuming, as we know. And this part is also, the main problem with this part is that a lot of times, or more often than not, it requires manual fitting. So it requires graduate student time. It requires somebody to actually sit down and play with the analytical fits. So it takes a lot of time. When I was a graduate student, I did a lot of fits like that, and it would take me weeks or months of my time to produce fits of potential surfaces for three-dimensional, four-dimensional molecular systems. Okay. Now I'm going to propose a crazy idea, and you'll see why it's crazy in a moment, and I'll also show you that this can be solved with machine learning, as a lot of crazy ideas they can be handled with machine learning. So the idea is, why not to approach the problem of constructing the potential energy surface in a conceptually different way? Why not to come up with a feedback loop that would start with a very inaccurate potential energy surface, and then that would adjust this potential energy surface through a series of cycles. Okay. Again, what we're proposing here is the potential energy surface observable feedback loop, and the idea is to generate a very rough surface with a very small number of ab initio calculations, and then have a cycle, then basically ask the following question. The question is where to add a new ab initio point in the configuration space, and how to modify it, because, like I said, the ab initio points, they will not always be error-free. Well, most often than not, they are. computed with errors. We want to be able to move those ab initio points in the energy space as well as in the configuration space.
Even the original points?
Even the original points, yeah. So the questions I'm going to ask is where to add in the configuration space this new point and how to modify it to achieve the most improvement of the quantum dynamics predictions. Because this is what we are really after, right? We're after accurate quantum dynamics predictions. Okay? Now, if we can do that, we get two things. First of all, we get the potential energy surface that only spans the most relevant part of the configuration space. Because a lot of times, if we just first construct the potential surface and then we use it in the quantum dynamics calculations, the potential surface is unnecessarily global, right? We always have to compute global surfaces, but the potential surface, if we do construct it in the conventional way, it's unnecessarily accurate in the entire configuration space. Whereas we know that depending on the collision observables you're looking at, some parts of the configuration space can be more or less important. So this approach would sample the part of the configuration space that's the most relevant for the dynamical process of interest. And second, you would get the potential energy surface. By construction, you would get the potential energy surface that results, when plugged into the dynamical calculations, that will result in a perfect match with desired observables. Okay? Now the question is, was there? Yeah?
What is the criterion to judge whether the dynamics is improving?
Well, let's say, I'm going to say a little more about that. So we want to design a method that gradually improves. So that at every cycle we have an improvement. And yeah, we can talk more about that as I get. What's that?
Is it compared to experiment?
Yeah, for example, if you have experimental data and you want to reproduce them, what you want to look at is the deviation from the experimental data, the deviation of your prediction, and you want to minimize that deviation. But there's also another way that I'm going to advocate. And I'll say more about that once I get there. So, but the main question I want to ask now is this at all feasible? Right? So, this feedback loop, is it feasible? Well, let's take a look at it. So, if we have an n-dimensional potential energy surface, and let's say we didn't use any machine learning or anything like that. Let's say we simply were to add an ab initio point and move it in that n-dimensional space. Let's say we discretize the n-dimensional space, use 10 points per dimension on the grid. So that would require 10 to the n calculations for each interaction, 10 to the n dynamical calculations for each iteration, right? For a 6-dimensional 4-atom chemical reaction, that would be completely out of reach. Now, the other problem, of course, is that at every cycle of this iteration, you would have to ask your student to manually refit the potential energy surface, right? So here you go. You would have, for a 6-dimensional system, you would have to do 1 million calculations, and you would have to readjust the potential energy surface manually 1 million times. So this would completely be unfeasible. So what I'm going to argue today is that with machine learning, you could, first of all, get away with, not with 10 to the n, but with 10 times n calculations. And there is no need for manual feeding the potential surfaces. You will get those potential energy surfaces automatically. They would be produced by the machine learning algorithm automatically, so you don't have to even look at them. So how do we do that? So we construct a multi-layer machine learning model. So we're going to use one machine learning model for the potential energy surface itself, and then we're going to use another machine learning model for the observables. So this machine learning model is going to be a function of this machine learning model, and this is what we're going to be after at the end of the day. We're going to want to produce the machine learning model, accurate machine learning model of the potential energy surface. Okay, and the machine learning model that I'm going to talk about is going to be provided by the Gaussian process regression. So I'm going to say a few words about what Gaussian processes are and how we use them. So a Gaussian process is simply it's a Gaussian random function, which is nothing else than a collection of an infinite ensemble of random functions that are Gaussian distributed around some mean function. So we have a bunch of points, we call them training points. These could be your dynamical observables, and we want to approximate them with the Gaussian process, right? So again, another way to look at this ensemble of points is it's a multivariate Gaussian distribution, right? In the absence of these points, we know nothing about these distributions, but we can now use these points. If we know these red dots here, we can use these dots to condition this multivariate Gaussian distribution.
So those red dots are like your initial guesses and where you...
These red dots would be my initial guesses of the quantum observables, so my initial calculation. I'm going to start with a very inaccurate potential energy surface, calculate, say, 20 points for a 3 or 5-dimensional potential surface, construct a very rough surface, calculate my dynamical observables. These would be my red dots, and then I would, through that algorithm that I'm proposing, I would improve the quality of the red dots. Okay, but let's say we have those red dots, the quantum observables, and we want to describe them with a machine learning model that's this Gaussian process regression. So basically, what it is, it's the model would be the conditional multivariate Gaussian distribution. So it's conditional because we know that it has to be a Gaussian distribution with width 0 right at those red dots. So basically, we have to construct a multivariate Gaussian distribution that looks like this. Okay. Now I'm representing this distribution by those gray curves, whereas in fact we never work with any analytical functions that represent this multivariate distribution. So all it is are distributions. So our goal will be to make a prediction of whatever we're looking at, say, in between these red dots. So to make this prediction, we're going to look at this Gaussian distribution at this part of the parameter space, and it's going to be set by the presence of all those red dots. Those red dots are going to condition this Gaussian distribution, and then I'm going to use the mean of this distribution here as my prediction. Okay, so it's a non-parametric method, and again, all it relies on is the knowledge of where these red dots are. Okay, now once I have my Gaussian process model, I can do wonderful things with it, and one of the wonderful things I could do with it is to use it for the optimization technique, quite often used in high-tech industry, called Bayesian optimization. Okay, and it's a beautiful technique. So I'm going to spend 2 minutes to describe it. It's a beautiful technique for optimizing complex functions that relies on something like Gaussian processes. So how does it work? So let's say we have a function, some multidimensional function that we want to optimize, whose maximum or minimum we want to find. So you would, within the Bayesian optimization approach, you would start by evaluating this function at a few points, like for example at these 2 points, and then you would approximate these points by a Gaussian process. So you would generate something like this. Okay. So then the question will be is where do I evaluate this function next? Okay. The steepest descent, the traditional steepest descent methods would tell you that, well, you should go in the direction of the gradient. Okay. But this method doesn't care about the gradient at all. We never evaluate the gradient, as a matter of fact, at all. So what this gradient relies on is the value of the mean of this Gaussian process. So you want to always go in the direction where basically you want to go where the value of the mean is the largest, but it also relies on the error of the Gaussian process. So when the Bayesian optimization algorithm looks at this Gaussian process, it will see, well, this point is bigger than this one, so I'd probably want to put a point up here. Okay, now the traditional, steep descent algorithm would get stuck there because it's a local maximum. But the Bayesian optimization algorithm is now going to say, well, I know a lot about the function here, but I don't know anything about the function here. So the error of the Gaussian process is going to tell the algorithm that you should go and evaluate the function out in this area here. So the next evaluation would probably be out here. And this will take you immediately out of that local maximum problem. Okay, and so this algorithm is very efficient. So it's extremely efficient, as you will see actually in the examples that I'm going to show. It requires no gradient of the function to evaluate. So it's ideal for functions that are difficult to evaluate because you need very few evaluations of the functions. Okay, and in our case, of course, this is going to be the case because these red dots in our case are going to be the results of the quantum dynamics calculations. So we want to do as few of those as possible. Okay. So I'm going to show a few examples now. And the first example, well, when you try to propose something new, of course, you want to do the simplest reaction system, which is the H plus H2 in chemical reaction dynamics. So I'm going to look at the reaction probability for this system as a function of the translational energy. So the black curve here is the accurate calculation with the full potential energy surface taken from the previous work. Okay. So I'm going to start with, so my goal is to get something that will be as close to that black curve as possible. So I'm going to...
Is this a J equals 0 cumulative reaction?
It is the J equals 0, yeah.
Cumulative?
Yes. Yeah. So I'm going to start with, again, I'm going to start with the rough surface that based on, say, 20 ab initio points. And so I wouldn't expect this to produce any accurate results. And what I get is the, if I plug that surface into the calculations, I get this dashed curve. And then I do this feedback loop, the optimization loop that I discussed, and then actually after just a single iteration, you get the green curve, and after only 10 iterations actually, so I'm going from 20 ab initio points to 30 ab initio points, I'm converging to the red curve here. Yes.
There's something I don't understand. You look at the observables and
Yes.
you adjust, but what they imply about what you do to the potential energies.
Every time I look at, I adjust, I change the potential energy surface. What?
I suggest that we give Roman at least 20 minutes.
Yeah. Okay.
Yeah, give me like 40 minutes, and then we can. Yeah. So I every time I run this cycle, I adjust the potential surface. I add a point in the potential energy surface, and by adding this point, and I'm retraining my Gaussian process model of the potential energy surface. So I'm adding the red dot on that graph, and every single dot on that graph matters. When I add a single dot, it's going to modify the global potential energy surface globally. And then I take that, plug that potential surface in the calculations, and after and then I get the dynamical results. So after only 10 iterations, I converge to the correct result. So I get the potential energy surface with only 30 ab initio points for this three-dimensional reaction system. This should be compared with 8,700 points that was used by the whoever designed this potential energy surface to begin with, and for these reactive scattering calculations. What's that? Oh yeah, I should maybe not listen to the questions. Sorry. Right. So if you may want to wonder, if the potential energy surface is physical or not. So this is what the potential surface looks like. Again, this is not an analytical feat, so it's not obtained analytically. It's a completely non-parametric surface. It's the mean of that Gaussian process distribution based on 30 red dots. So it looks completely physical. So we were actually hoping that in this process we would get correct dynamical results with some crazy potential energy surface. We were hoping to see that because that would be cool, but crazy. But but we never actually saw that. Every time we would converge to the correct dynamical results, the potential energy surfaces would also converge to the correct potential surfaces. Maybe it's because we're looking at systems that are not too complex. Maybe once we start looking at Joel's systems, we will see some of the craziness, which I would actually like to see, because that would imply that I can describe correctly my dynamical results with potential surfaces that are completely, crazy. I have yet to see that. Now, we've also done more calculations for bigger systems, like the OH plus H2 is a 6-dimensional chemical reaction, and in this case we changed the human to graduate student here. So the previous calculation was based on the potential surface actually fitted with a neural network based on 17,000 ab initio points. Now we obtain. So the black result is the accurate result obtained with this potential surface. We obtain the green curve with the surface based only on 290 ab initio points, placed in that 6-dimensional configuration space. Now, in both of these calculations, we're minimizing. When we run those optimization cycles, we're minimizing the difference between the black curves and whatever we're getting at the output of our dynamical calculations. But what if we don't know? So what if we don't know the accurate results? Can you still converge to the same surfaces? And the answer is yes. So the idea here is to maximize the difference between two successive iterations. And the idea relies on the fact that as you include a very large number of points in your potential energy surface, we know that this is guaranteed. Well, this method, the good thing about the Gaussian process regression is that it doesn't suffer from overfitting. So we know that in the limit of the infinite number of ab initio points, we're going to converge to the correct potential surface. So the infinite number of points limit converges to the correct dynamical result. And so therefore, if you maximize the difference between two successive iterations, you're going to get to that correct result the fastest. So that was our assumption. Well, that was our assumption, and that's what we see. So in this calculation, I want to emphasize we do not use the black curve in any way. So the black curve is where we want to be. We do not use the black curve at all. Again, we start with 22 points, not 20, but 22 points in the potential energy surface. It takes a little longer to converge to the black curve in this calculation. You have to go all the way to 70 ab initio points. So you have to go through about 50 iterations in that cycle. But you do converge to the results shown by those red dots here that basically are indistinguishable from the correct results. And again, I want to emphasize again that we do not use the black curve in this calculation at all. All we're doing, we're maximizing the difference between the quantum dynamics observables in the two successive iterations of that optimization loop. Okay. Now, just to illustrate that you can feed anything. You can feed an elephant with this. So we took these original reaction probabilities and we modified it randomly. So in particular, so we generated this dot dashed curve here. So the most importantly, we displaced this curve along the energy axis right here, which implies that so if the reaction probabilities were described by the dot dashed line, that would imply that the potential energy surface that gives these reaction probabilities has to have a higher activation barrier. So there is more activation energy to get these reactions started. So we wanted to see if you can, then if you plug this dot dash curve in the calculations, you converge to it, and then what we get is the green curve after about 30 iterations. So we run this cycle for 30 loops, and we converge to this curve. And again, you look at the potential energy surfaces; they all look physical. Am I out of time already? But I was interrupted, right? So just again to convince you that what we're getting at each iteration are the surfaces that are physical. This is what you're getting. And again, I want to emphasize that these are not analytical feats. These are simply means of this multivariate Gaussian distribution. And again, another important point is that you get these potential surfaces completely automatically. You do not have to do this manually at all. Basically what you're doing in this process, you're sampling over a very large number of these sort of potential surfaces. Every time you add an ab initio point, you're going to change the global surface, and you generate a lot of them automatically, and you're sampling from those surfaces in a very efficient manner. Okay, right. So what I've talked about today is a class of kernel methods of machine learning. And so we're very excited, in particular, about the applications of kernel methods, because neural networks have been used, for a variety of applications in molecular dynamics, but not kernel methods, to the best of our knowledge. And so we can talk about the differences in the Q&A session. So I just want to very briefly mention some of the other applications that we illustrated. So we've been looking at this for about 3 years now, and we've written a bunch of papers. Of course, the most obvious one was. One of the first ones we looked at is fitting potential surfaces themselves. This is the most straightforward application of machine learning, and neural networks had been used for that again by a number of people. With this approach, the fitting is very efficient. You need very few ab initio points. If they're sampled properly. More importantly, this approach is completely general, so we use the same code for any molecular system, for any dimensionality. You don't need to change anything. And so there is zero amount of physical work that goes into producing those potential energy surfaces, which I think is useful for all of us. And it's very easy to code because there are lots of packages available online. Okay. Now. So once you have these Gaussian process models trained, basically what you have a model that's a function of potential energy surfaces, potential energy surface parameters. So you can do the sensitivity analysis. You can actually look at which parts of the potential energy surface are more relevant for whatever observable you're looking at, or less relevant. So I'd like to think about it in terms of this sort of molecules. In the future, we want to take it to describing interactions between bigger systems. And then, so if you have an interaction of big molecules, and you do it this way, then you can start asking the question of which pairs of atoms, the interaction between which pairs of atoms matters for the outcome of the interaction between these two species the most. Okay, a bunch of other applications. So of course, one of the biggest questions is, that we've been thinking about is what is the effect of the inaccuracies of the potential energy surface calculations on the dynamical observables, and so using this methodology, you can obtain scattering observables averaged over potential energy surfaces within their uncertainty. You can actually use this approach to put error bars on the dynamical calculations in a meaningful way. And I'll say more about what I mean by that if you ask me during the panel discussion. We've also used it to use classical trajectories to interpolate between quantum results, because there's correlations between classical and quantum results. So you can train a machine learning model on the correlations between classical and quantum results. So you can use this to obtain converged results from unconverged calculations, extrapolate scattering observables from one molecule to another. What we've talked about is a version of the inverse scattering problem. I guess I'm not going to say that. Let me just, what I want to say in the conclusions is, well, just a few things, right? So I believe that the combination of machine learning with quantum dynamics, well, first of all, it makes computations a lot more efficient. I showed you that it can be combined with Bayesian optimization, which is a very, very, efficient method of optimizing complex functions and functionals. It can be used to evaluate error bars of the dynamical calculations. I would say in the proper way. It can be used to analyze the role of individual atoms in determining the encounter of complex molecules. What I'm particularly excited about is that it can also allow us to ask new, previously unimaginable questions related to molecular dynamics, and that's where I think the most power of machine learning is. Well, I think I'm going to really stop here. So I just want to mention the names of my group members who contributed to this work. Originally started with Sous. She's now working in high-tech industry, obviously, and she was a data scientist at Bank of Nova Scotia, and now she moved on to higher positions. And Rodrigo Vargas lately has been a very important student in this effort. So these two papers were very excited about. I didn't talk about this at all, but people like Lincoln might be interested. So I hope we could talk about this, before the end of the day today. Thank you very much, and sorry for going over time.